Swayam Prabha. Digital India. Educated India.
Okay, so we'll start. So welcome to day 5, last day of this course. So just very quickly, we first 2-3 days we talked about basics of AI/ML. Yesterday we spent a lot of time on deep learning methods, different types of deep learning methods, and also in different fields. Okay, again, these methods are doing really well. They are among the top performing methods, especially these deep learning methods. Also, given the data set sizes have increased a lot in the last couple of years, and whenever data size increases a lot, that's when you will see the deep learning approaches also start performing among the best models. Okay. Today we'll see a slightly different flavor, not deep learning methods, but a little bit different flavor of how these AI/ML methods can be used to guide experiments. So in today, what we'll see is a synergy between AI model and an experimentalist, so to say, how they can work together and in what format they should work together to exploit these methods. And also this synergy will be in an iterative manner. It is not just model says do this and that's the end of the story. It will not be like that. It will be iterative. Model will say, experimentalist will do, experimentalist will now tell the model, model then will again tell the experimentalist, and so on. So it will be an iteration sort of a thing. Okay, so let's get started. Okay, so first thing, so far what we have been learning is type of models which are a point estimate, meaning for a particular given x, the model was predicting a y, right? But we will switch over to models which will give a distribution of y. So what I mean by that is, we earlier talked about such type of model, right? There is a function which takes input as the features and gives output y cap, right? So importantly, y cap is a point estimate, meaning it's a single number, right? It's just one number. But now what we will try to do is, we'll again try to give in this same thing, but instead of y cap, I'll get a distribution of y which has mean mu, and then you can say variance or sigma, whatever. It has a mean of mu and variance or standard deviation of this sigma. Okay. In other words, we were always drawing these parity plots, right? So this may be my ground truth data, this is my model prediction, and we were seeing that, okay, this is how my data is looking like, especially for the test set case. But now instead, for every point, this is again my y. Remember, y cap is now a distribution, which means that not only I am predicting mu cap, I am also giving a variance window. So for example, for this case, this thing is my sigma cap. Okay. Other way I can plot the same thing is, now on my x-axis is y cap, okay, and this thing is a distribution with this point being mu cap and this thing being sigma cap. Okay. My one single prediction itself is a distribution with some uncertainty window or some standard deviation available to it. Okay. And the same distribution, I am plotting it like this on this plot. Okay. What is this thing called? What should be the y-axis in this case? X-axis is my y cap. So, for example, I am talking about hardness of an alloy. This thing will be, this scale will be Wicker hardness. What will be this scale? Again Wicker hardness, whatever property you are talking about. Okay. What is the y scale?
Frequency of occurrence.
Yeah, frequency of occurrence sort of, but the correct term is probability distribution function. So, the correct thing is it's a PDF. Okay, this is probability distribution function. Okay. So, generally students come and ask, right, what are the courses that I should take to learn machine learning? So, the two main courses you have to do before you get started into all machine learning area, first thing is linear algebra and the second thing is probability, okay, probability theory. So, to better understand what is on the y-axis, you have to know what is a PDF, what is a probability distribution function. So, little bit mathematics of that you have to know. Okay. So, now as you can see here, this is previously the type of models we were making on the left side, and on the right side for each of the output I now have error bars, right, error bars, uncertainty window. More correct way to say this is the sigma, the variance that has been predicted by the model along with the mean, which is your mu. So, the solid symbol is just suggesting the point where mu is, and the error bars is suggesting what is the uncertainty window or the variance in the model. Okay. So, first thing we have to do is we need to, instead of an point estimate model, we need to move to this models that can output distribution, okay, and can predict this thing. So, what are the models? What are the type of machine learning models that can give you a distribution instead of a point estimate? Ensemble models, yes. More simpler. Yeah, random forest is also depends on how you do it. Yeah, depends on how you do it. Gaussian. Yeah, so Gaussian based models. So, Gaussian process regression is one of the most famous model which has a formal basis for this uncertainty. Okay. So, Gaussian process model is a very popular model in this case, but I do want to let you know is that there is also something called Bayesian linear regression, which will also give you similar thing. There is also Bayesian networks. So, how deep neural networks, like common neural networks that you studied day before yesterday, how they can also be made in a Bayesian manner to result in such type of distribution outputs. Okay. Not just that, any model that you have, say a linear regression model also, you can play around with the training data in such a manner so that you are able to use simpler linear regression models also to output error bars or uncertainty windows. That is done formally using this bootstrapping approach. So, bootstrapping is also a statistical approach through which you can convert any point estimate model also to return a uncertainty or an error bar. And then ensemble approaches are also somewhat similar, which used to return this uncertainty windows. Okay. Yeah, so we will see that why this information becomes important. Okay. One more point you want to notice, maybe it's visible or maybe not, but some of the error bars are smaller in size, some of the error bars are larger in size. So, what does that mean? So, the model is more confident about some predictions versus some other predictions. Okay. It is not a constant variance for all data points. Depending on what data point, the variance will be different. Okay. So Gaussian process regression, so I'll not go into the mathematics of what are the derivations of GPR model. So it's called GPR in short. This is how the predictions may look like. Okay. So all the blue points that you see, they are your training data. The orange line or the yellow line that you see, that is the mean, the mu cap. So if I am talking about, say, some point here, this orange line is my mu cap, okay, yellow line here. And what is the shaded region telling me, the yellow shaded region? The variance or the uncertainty for that particular region, okay. So do you observe anything about the shaded region? Any behavior of the shaded region? Yeah. So some areas the shaded region is large, some areas it is small. Okay. Where it is large, where is it small? When?
First there is lack of points, but where are there points like the fitting is not very good.
So how do you know fitting is good, how or not good?
Overlapping of basically the data.
So okay, one more important observation: does the model always pass through the blue points? The orange line, the yellow line, does it always pass through the blue point? Okay. So what it is telling you, that training data, it is perfectly fit. The error on the training data is 0. Okay. So that is one more thing you have to observe. Now around the training data, what do you see about the shaded region? The uncertainty is very less. So which means the model is very confident around the training data, and the farther you go from any training point, the model will be extremely uncertain. Okay. So let's first take this part, right? On the left side of this blue point, there is no training data. So that's where the model is totally uncertain. Between these two blue points, somewhere around 5 and 8, around 5, the window is smaller, then it starts growing, but then the moment it starts growing, then the next training points become a neighbor, like the distance reduces, and so again that the uncertainty reduces. Okay. So so her question is, so that's a very important question, is important to understand this, why the blue dotted line, which is my ground truth function, okay, that is the function I am trying to learn, why the model is, why the blue and the yellow line do not coincide. Okay. Basically why my model is not able to learn the ground truth function. Okay, that's her question. Any answers?
We don't have enough data.
So the one thing you have to realize is ground truth functions, although in this toy example is shown, it is always unknown. That is a very important point to understand. Ground truth is always unknown. In these toy examples, yes, someone is showing it to you. Okay. But if I ask you, what is the ground truth function that gives me hardness of an alloy? We don't have that. Okay. Any material science problem, we never have a ground truth function available to us, except in those cases where solving, say, Schrodinger equation. If we think that Schrodinger equation is the absolute ground truth, and if that equation you are able to solve, then maybe you have the ground truth thing available to you, but otherwise we never have that ground truth value available to us. Okay. So the blue dotted line, to a certain extent, you should ignore. It is as if something, it's not even available. Okay. So yeah, so main observation here, depending on the distance from the training data, the uncertainty of the model is larger. Okay. And these are the types of models. This is how the uncertainty behavior of these models appears to be. How do they behave? Okay. So
Yellow line is a kind of baseline model, or this kind of mean prediction is written, right?
okay, so what do you, baseline model, we were always talking in the context of mean or average prediction. So what would average baseline model look like in this particular case? Yeah, it should be horizontal line wherein all the blue points you take and just take a mean of that. So somewhere around here maybe that horizontal line is your baseline model. Okay. Okay, and then again just reiterating, the shaded region is your uncertainty, the error bars, and this black square that I talked about is the mu cap for this particular given x. Okay, so now given this context, let's also see how a typical materials problem look like, right? So generally we always have some known data set. Okay, so some materials are always known to us, their properties have been either experimentally measured or some DFT calculations are done, some MD calculations are done. Maybe for 20-30 cases calculations are done. Okay, for those say the experiments are done. Okay, but we always have a large candidate data set. So the space of alloys is really large, right? I mean, so many alloys can be made. We have only tested a small fraction of it. Space of polymers is very large. We have only tested small fraction of it. Similarly, any space you take, molecules, surfaces, 2D materials, oxides, inorganic, whatever. The space is always very large and only small fraction of it is what we have experimentally measured. Okay. And so what we want to do using our machine learning methods is, given this known data set, I will go ahead and make a model. So last 3-4 days, whatever you have learned, all types of models, you can go ahead and make them. Okay. Using those models, what you will do is you will make predictions for all this candidate set. Whatever candidate set results in the best prediction, you will basically try to make that in the lab or do your calculation on it to check whether that prediction was a good material or not. Okay, this is usually how you will go about doing things, right? So does that sound good? So basically this is what I'm saying, right? You start with the known data set, you train the model, you predict for all your candidate data sets, okay, and then you perform experiments on the best candidate. Okay, does that sound okay? Okay. When I say train model here, whatever you have learned so far, everything is encompassed here. Whatever fingerprinting techniques, whatever different types of ML models, whatever you have learned, everything is encompassed in that box. Okay. Okay. So what are the issues with this approach? What do you think? What is the issue? Is there any issue with this approach? Okay. So she is saying that say I am looking for high hardness alloy or high band gap material. I have one candidate here which is extremely high hardness, extremely high band gap, and in this candidate set I do not have any material left, candidate left, which is higher hardness than available in this data set. So if you think that okay, there are two things. The output for this candidate is only a prediction, right? We only have predictions for this. The prediction from these candidates may be smaller than what is available in this training data set. So that is still possible. Okay, but even then you can go ahead with whatever the machine learning suggests to be the best, the top predictor. It may be smaller than the training data, but machine learning can still recommend something that among these, this is the top candidate, so go ahead and make it. Okay, whether the actual experimental value of that candidate is better than training data or not, that we have to check. Okay, but still whatever ML suggests the best candidate, you can go ahead and make it. Okay. Let's look at another scenario where say somehow I know the true values of these candidates also, and I know that my training data has a better candidate than any available in this candidate data set. Then what will we do? Then actually there is no point of doing, right? Because you have chosen a candidate data set that is already worse than what is available in your training. So your problem statement itself is not good. Okay. In other words, you already know this is my best candidate. So what is the point of doing more experiments now? Okay. So we are always looking for such problem statements in which the candidate space is extremely large. Okay. So just to give you some context, say this space is of the order of 20 to 30 data points. I am talking about this space of the order of 100,000 or 1 million. So the order of magnitude difference between them is like 3, 4 or higher. Okay, so much larger space I am talking about. And if because the candidate space is very large, we expect at least some candidate is there that is better than our training data. You are saying that because this is small, the candidates in this may be in the extrapolative regime, right? Okay. So yeah, so that's a fair point. We will remember this question and we will ask ourselves, is it bad or not? Is it a bad thing or not? We are using model in an extrapolative regime or not? Okay. I think someone already gave the answer back there. What is the issue with this approach? Yeah, they said uncertainty. So now do you want to expand that? See, so far whatever training model prediction we are talking about, we are not talking about the confidence interval of the model. Okay. So not only it is important to take those candidates which are predicted, which the model predicts to have good properties, we also have to check whether for those predictions is the model confident or not. Okay. So in this entire approach, the uncertainty or the confidence interval of the model is not taken into consideration. Okay. Another very important issue is that my data set is very small. The initial model is trained on very small data set. So my performance of the model is expected to be actually poor. Okay. And this point is somewhat related to his earlier point. Because this data set is small, there is a high chance I am always doing extrapolation for this candidate set. Okay. So and that's another way of saying my model performance is poor. Model performance poor means that you are mostly doing extrapolation only. Okay. And then there is another thing like what is the definition of best candidate? Okay. So what is my best candidate? Is best candidate the one which has the topmost prediction, or is it the one where model is confident? So what is the definition of best candidate? Okay, that is another thing that we should define well. So this is where active learning comes into picture. So what we do is we start with a known data set, the same data set that I had earlier. We train a model, same thing. We make model predictions, also the same thing. Based on these model predictions, I select some best candidate. I'll define what is best. Okay, we select some best candidate, and for that best candidate, we actually go ahead and do the experiment. That experiment output, we put it back into the data set. Okay, now my data set, say it was earlier 30, now it has become 31. For this 31 data set, I again train the model, again make the predictions. The second version of the model trained on 31 data points is better because it has more information, it has better training data. So using that, I again make the prediction, do the experiment 32. Now 32 is my data set size, again train version 3 of the model, I keep on going. I keep on doing experiments in a guided fashion as determined by my model in an iterative manner. Okay, and because of my iteration, because I am adding the experimental data into my data set, my model performance is also increasing. So version 1 is supposed to be better than version 0, version 2 is supposed to be better than version 1, and so on.
Those data points previously there, right? In their known data set.
The known data set keep on increasing because now you have performed more experiments.
We are doing experiment.
So you did experiment here. Say
on the data which is already there in the known data set, right?
no, something that is selected from the candidate set. From the candidate set. Yeah. Okay.
What if the experimental data, the new data is say not much different to the existing data?
What if the new data is very different from the,
Very different.
not much different?
Not very different or extremely different from the previous.
So this question is similar to saying what if the training data contains similar points or different points? Okay, because your training data is something that is getting changed. Okay.
In the sense, like, say, the model has actually predicted something that it will be of this sort.
Hmm.
But when we get something which is in the extremities of the
Hmm.
data set, it may mean that what is being predicted itself may not be very accurate.
Okay, so I think you're saying that say model predicted something, we did the experiment and the prediction is very prediction, the error on that was really large. Is that what you're asking? So model prediction was very bad. Is that what you're asking?
Sort of.
Model predicted something to be, say the model predicted it will have very good hardness. We went ahead and do the experiment and realized it was very poor. I mean the hardness was very low. Okay, so model prediction was extremely bad. Is that what you're saying? It doesn't matter, you still go ahead and add it into your training data. Okay, there could be reasons why the model prediction was bad, but as long as your experiments are done in a proper manner, the training data is your ground truth. It is as simple as model tried something but failed miserably. But the next time you will make the new version of the model will know that alloys of those composition are actually very poor, which is different from a previous understanding, which is from the previous understanding of that model. So this is how iteratively the model is also improving. Okay. The only important point is that the experimental data that you are adding should be correct. It should not be the experiments are done poorly and you are adding just noise into your data set.
So that the model is always fixed. They are not changing.
No, we are, you mean, no, model is retrained. So that training step that you,
The model GPR we are using, every time we will be using.
it is mostly people prefer just one model for simplicity, but there is no restriction like that. You can even try to change the model. Okay.
When we need to stop?
Yeah, so that's a very important point. When we need to stop, there are no good answers there. A way you want to stop is that, say you already found a candidate which has the performance that you are looking for or the property you are looking for. Say I wanted Vickers hardness of the order of 800. I already found something, so then I'll stop it there. And say you can do 10 experiments or 20 experiments, you did those 20 experiments, then you stop there. We can start looking into the error that the model is making, error of version 1 versus version 2, version 3. If the error sort of saturates or goes down to the level that is acceptable to us, that's when you can stop. So there is no one single answer, single good answer. Yeah. The more you do experiments, the better your model will get. And ultimately, if you can do experiments on your entire candidate set, that is the best thing. Right? But that doesn't make business sense in that way. Right? You will spend a lot of money for not much.
The quality of model also, like which kind of model you are using for prediction also matters.
Yeah.
We were doing
So what people would generally do in this box, they will try everything. So for example, you ran a script yesterday, right? Wherein I think random forest, gradient boosting, SV, I don't remember what all. Some 4 or 5 models you checked, and then, so given this data, you try all the models that you think are resulting in the best accuracy. Whichever model with whatever hyperparameter is resulting in best accuracy, you go ahead and select that model only to make the predictions for this data set. Okay. So again, everything you did until now is encompassed in this box. Okay, your fingerprinting, model testing, whether you want to use traditional ML approaches, deep learning approaches, everything is encompassed here. Okay. Okay, why it is a better approach than what we previously discussed? Because your model is getting better and better. Why it's getting better? Because you're adding more data in an iterative manner. Okay, So see how iteration is also guided by the model, right? Every experiment that you're doing is guided by the model, and that is what it makes it more efficient. Okay. And yeah, model performance is also increasing. So now comes the second important point. What is the definition of best candidate? Okay. In here I just skipped through that part, that I'll select a best candidate and do the experiment on it. But what is the meaning of best candidate? Okay. So let's understand this using an example. Okay. So just like we had blue points there, I had green points here, which are my training data, my observation. I am again fitting a GPR model on top of it, and the red is a true function. The red dotted line is a true function. Something like x sin x. I don't know exactly what function it is. This is my true function, but we have to remember true function is only for educational purposes. It is never known. Okay. The red dotted line is unknown to me. I'm just showing it for educational purposes. Okay. Now, given what is this green dotted line indicating? The GPR mu cap, basically prediction of the model. Okay. My candidate set is basically my x-axis. Any point on the x-axis is my candidate set, and I want to find that x which results in maxima, which results in maximum of this target property. Okay. The model predictions are this, which is available to me. Based on that, what I'll do is I'll select the candidate which has the highest predicted value. Okay. So what is that? That will be this particular x value resulting in this blue point. Okay. So because this is the point which has the highest predicted model value. Okay. That is what I have selected. Okay. Is that a fair approach? I selected that candidate which has the highest hardness, right? Which has the highest property. That's what I have done. Is that fair? Okay. So let's see if we'll see what will happen. Does anyone know what issues we'll run into if we do this? Okay, let's not. So let's see what happens. Okay. So iteratively we have to do, active learning we have to do. So I selected this point. I selected this blue point. Then what I'll do, I'll go and do an experiment on it. Once I do the experiment, I'll get a value. What will be the value? The value will be the red dotted line value, the y associated with the red dotted line. So now, and then I get that value and add it to my training data set. Now that point has become a green point. Okay, the observation has been made. Given this observation, now my new GPR model, I'll again go ahead and train the model and then again select which is the topmost prediction. So my new GPR model becomes this dotted line. Again, I look for that point which has the best predicted value, the highest predicted value, which is this particular x shown by the blue symbol. This is my model prediction. I go ahead and do an experiment on it, basically get the red dotted line value associated with that point. I get the value here and I keep on doing it. Okay. So what do you guys observe? What is happening? So this is iteration 1, 2, 3, so on.
It's getting stuck there, like that uncertainty is not decreasing the other side. It is not able to learn that part.
Oh. So what he's saying is that it is stuck in this local, I mean it's not even a maxima. It is local maxima from the perspective of the GPR, but it is stuck here. Okay. It is not moving in either this space where there is a high value possible, nor this space where there is a high value possible, right? The GPR is getting stuck. Okay. So if you just, so what is the point here? If you only rely on the highest predicted value, your models could be stuck in a specific composition range of the material. Okay. The model will not be able to explore something beyond what it believes to have the giving better results in a particular composition range. Okay. That is the issue with this thing.
It is actually getting local even after training.
Yeah, you can keep on training. The problem is look at the green point, right? The green dotted line is the information available to us, right? So from a green dotted line perspective, it has actually found the best candidate. But we know that there are other spaces possible in which if it would have explored, it would have done better. Okay.
But in the training, it did not happen.
It is not happening. It is getting stuck. So this is the problem with selecting only the top predicted candidate from a machine learning algorithm. And therein comes the next point, which is in entire this thing, do you see any shaded region? There is no shaded region, right? Basically, I did not use any uncertainty, any confidence of the model. I only talked about what is the best, highest predicted mu cap, highest predicted candidate. And this thing that we are using is called exploitation. And if we start using the uncertainty of the model, that is called exploration. Okay. So, so how can we use the uncertainty? So let me explain this again with another toy example. Yes. Yes. Say there is a material for which you are not able to featureize. Yeah, so then it means either the material has to be removed or that particular feature column from the training data also you have to remove. That is why whenever you are doing featureization, right? We did an exercise. That was the purpose. I always talked about can for a candidate set you can create a feature or not. Yeah. We are exploiting the model's information, like the model information meaning what is the highest predicted mu cap, just based on mean. So maybe it will get clear from this example also. Say somehow I am able to condense my entire whatever material space. Say you are in alloys, so all my alloys are on x-axis, polymers are on x-axis, or whatever space you work in, somehow it's all condensed on the x-axis. Y-axis is the property you are looking for, some score I have given. Okay, it could be multiple properties also combined in a single metric. Okay, always some materials have been tested. For those materials I know what is their score. So the blue points are indicating what is the scores for some of the materials I have tested so far. So this is basically my training set, right? Known data set. I need to decide what is my next material for which I should do my experiment. Okay. Two ways I can decide. I know that these are the type of materials which are resulting in high score. So let me try and change their composition little bit so that maybe I'll find a material which is better than this one, right? We usually look at the periodic table and try to do such sort of a thing. Okay. Other thing I can do, if I want to go crazy, right? I'll say that okay, for this space, this property has never been tried out. Let's measure it. Okay. So I have no idea about how would this type of material space do. So let's measure this thing. Okay. If you do the experiment in this thing, it's called exploitation, because you know that this composition space is already good and I'll just slightly modify it so that it results in slightly better property. If you do your experiment in this space which is totally different, that you can think of it as exploration, right? You are exploring, you have no idea what will happen there. Any method of search should have both components of exploration and exploitation. Okay, neither of them is a good approach. None of them is a good approach. You need to use both of them together, and that is what will make a good search algorithm. Okay, if you look at how animals look for food, you should just read up on that part also. They also do something like this: exploration, exploitation. So they have sometimes they search in a very local space, very short space, they look for food, and sometimes they quickly go to a very far distance and try to start locally searching in that space. So there are long distances traveled, followed by some local search. Okay, so some exploration, maybe something is out there because we have never checked it out, and some exploitation wherein you locally try to search that, okay, because finally you need both to find food for them. Okay. One more important thing, whether exploration will help, whether exploitation will help, we never know the ground truth function. The dotted blue line, which is my true function, is always unknown to me. So I do not know before I do the experiment what will help. It could be either. Okay, because it could be either, that's why we need to do both of them. So which means that in fact any global search optimization algorithm, right, whether you are talking about genetic algorithm or you are talking about Monte Carlo tree search, I don't know if some of you have heard about it, whatever, any global search optimization algorithm, you will, if you look at their equations, you will see some form of exploration and exploitation, their balance will be there. So all these global search optimization algorithms try to use this underlying concept. And this is exactly what we will be using here as well.
Sir, if you don't mind for a minute, can you go to the previous slide where you are talking about exploitation, like in the local region?
Yes.
Few slides before.
Yeah. This slide only or no? Okay.
Yes, this one.
Yeah.
Yeah, so here features are materials, right?
Yeah. So x-axis is features or materials. Yes.
How did we order them? Like,
Yeah, very good point. So how did you you learned about some PCA or feature selection, this type of things, right? Feature reduction. Okay. So somehow you have condensed all your features. Say your feature was of the dimensionality 1000. Somehow you condensed it into 1. So this is how it's done. It's again a mapping. It's again a mapping. It can be done in an unsupervised learning manner. You can do it through some other way also, but somehow it is done. Very simply, you just took PC1. That's how you did it. PC1, you're familiar? Like principal component 1. Yeah. That's one way of thinking it. I think Kamal was mentioning TSNE. Just take one component of TSNE, that's another way you can do it. One component of UMAP. Okay, so now given that we need to use both exploration and exploitation, we will start looking at how should we define my best candidate. Okay, so exploitation meaning basically just selecting the best candidate with the highest predicted property, highest predicted mu cap. Exploration meaning you are simply looking at the highest uncertainty, so highest sigma or highest variance. So that is another way you can do it. There are two other things that we'll see now, which is probability of improvement and expected improvement. So these things, all these things are also called as acquisition functions. So there are different acquisition functions. There is still ongoing research on it. People continue to develop new acquisition function. We are just learning a few of the basic ones. Okay. So what is this probability of improvement? So yeah. I plotted this thing, right? Yeah, I think it's okay. I think it's there itself. So now next what I am doing is along with this blue point, going back to the same toy example, right? We had this green dotted line, 3 observations were made, and then this blue point is the one which is the highest mu cap. But along with the mu cap, actually I also have a distribution, right? And this is how my or uncertainty, and this is how my uncertainty distribution looks like, the blue line. Okay, which means it's telling that there is a large variance sigma associated with this blue point. Why this should be large? Because it is far from both the training data points, right? If I look at this site, say I was looking at say 1.5 x value, there also it will be large. Okay, the uncertainty will be large. Now what I will do is I will define something called as probability of improvement. So what is my current best in the training data? What is my, I want to maximize, right? We want to maximize. So what is the current best value that I have so far? Sorry? So basically what I need to do is I need to look at the highest green value, the green circle. So the value associated with this green point, that is the best candidate I know, so the best known material from the known data set. Okay. So I will plot a horizontal line here, and from that I will check. So if you see, the blue line is the shaded region now is associated with this current best, and you look at area under the curve associated with anything above this current best value. Okay. So basically you integrate in this area. Okay. Is that clear?
Can you please repeat?
Yeah. So what is my, let's see if I have, okay, let me draw it. Okay, so this is my one green point, this is another green point, okay, and this is my, the highest predicted candidate. Okay, what is my current best? It will be, this is the current best value that I have. Now associated with each x value I have an uncertainty. I mean, I'm not plotting all shaded region, but there is an uncertainty associated with it. So what is the uncertainty associated with it? Something like this, okay, where this thing is my sigma. Okay. Now what I will do is I will take this thing and integrate everything above this. So this shaded region I will integrate, and this thing is my probability of improvement. This is the current best, so I will improve above it, and I am accounting for the uncertainty that I have. Coming back here, right, if for this point you plot the distribution like this, what it means is, say this thing is mu best, this value is mu best, so this line is telling me what is mu best, this point is telling me what is mu best, and I need to go and integrate all of this region for this particular point to find my probability of improvement. Okay, is that clear?
The probability of improvement is same as Q distribution.
What type of distribution?
Q distribution.
I'm not sure, I'll have to look at it. Yeah.
Sir, one more question. To get the best possible prediction, we have to search through the whole search space, right?
Yes. So now I only showed for one case. For all x values, you have to do this thing.
So for each iteration of active learning, you have to do one prediction for whole search space that you have not.
Yes, yes. So for your entire candidate set, now you not only need to have mu. Earlier we were only looking at mu cap. That is the best prediction. Now you need to look at mu cap. You need to look at sigma cap. You also need to compute this probability of improvement. So for all your candidate data set, you need to integrate and get this probability of improvement. And based on highest probability of improvement is what you will select the candidate. So how does it do both exploration and exploitation?
Probability during the exploration
Hmm.
will explore already it is based on the highest exploration point.
So this line is defined by my, is sort of my exploitation line, right? Whether I'm doing better than this or not. This area under the curve is telling me about exploration. How much is the uncertainty for this thing? Okay. So this is how both exploration, exploitation concept is there.
Still local to the predicted maximum.
is this.
We are still looking for the region closely associated with the
No, so what I am saying is this is just one case. For this case, this is how you will compute. At this point, again there will be a point. For this also you will have a distribution. Okay. For this case, the probability of improvement will be nothing but this area. So for all x values, you need to compute probability of improvement, and based on that you decide.
So you said like if we don't pick the best candidate, that we can match true function, right? Like imaginary. I mean, there's a chance.
If we don't pick the best candidate, what do you mean by best candidate?
Like the highest
Okay. If you don't pick the highest candidate,
in active learning, you said issue with exploration,
Ah.
exploitation.
ah,
You said we may match true function, but we don't know the true function, right?
yeah,
But let's say if we have candidates and then we some like hypothetical algorithm which computes everything, possibility of everything. Like let's say we have a list of candidates, right?
ah,
And then we add it to the database and then we train and then we took another prediction from our first prediction and we train it and then we keep adding this. So we can have a data and then if we map it, we may able to predict the true function, right?
okay. So I think let me repeat it so that I think I understood or not. So you are saying you took the model, you made predictions for everything. The highest predicted candidate you put back into the training data. When you say put back, you put the prediction or the actual value.
The prediction value. So
The prediction value you put, you didn't perform the experiment.
I didn't perform this.
You didn't perform the experiment, you put back
Yeah.
the predicted value. Now your training data set has still increased, right? Now again you made the model, okay, and then make prediction again. So basically instead of doing an actual experiment, whatever the model predicts, you put it back and then train the data, train the model again. Okay, so what do you guys think? Is it a good strategy?
Model. So I'm not asking like only picking the best candidate. You said, I believe you said, or I misunderstood, that if you don't pick the best candidate, there's a chance that it may match the true function, right?
If you don't pick the best candidate,
It may whatever the part like reaches the true function.
if we don't pick the highest candidate, then it may match the.
Match or like
Okay, I'm not sure if I'm following your question. Anyone else following his question?
But how do we match if we do not know the truth?
like that's why I'm telling you that if we predicted everything, every possibility, like we may have the chance of predicting it. Like, is it feasible?
No, we anyway predict for everyone. I mean, anyway, for the candidate set, you will make the prediction because these models are very cheap. You can quickly predict. So that is not an issue. But I think we should talk later. I'm not able to follow your.
Framing it properly.
He is telling that whatever the model predicts for the candidate set, that we treat as another ground truth and add to the.
That he is saying, but okay. Say we take the model prediction as the ground truth and add it to the model to retrain it. What do you guys think? Is it a good strategy?
Testing on the all data.
Yeah, it's not a good strategy because your model itself is bad. You also know it is not good, right? Because it's trained on very small data. And then if you start treating that as ground truth, you are just further increasing the bias in the model, meaning it is already bad and you are just giving it wrong inputs now. It will. But having said this, there are some situations in which we actually do this, not completely, but only for say 2-3 scenarios. I mean 2-3 iterations we do it, and so there are some examples where we actually follow this strategy, assuming that model is decent enough. Okay, so sometimes we do that also.
So, like after we get the probability of improvement, are we going to train the model by performing after like one experiment we perform? And
We'll see it. We'll see it. Okay. So let's go for. So let me quickly just introduce the formula. Okay. We'll not solve it. So fx star is nothing but the dotted horizontal line, which is your current best. Okay. Okay. It's not so important. Yeah. What I wanted to show here is that there is a analytical form by which you can compute probability of improvement. Okay. So whenever there is an analytical form, it means that you can quickly compute such a thing. Okay. So that's the main thing I wanted to show here. And in here you also see concepts of what this big phi is, basically cumulative distribution function. So that's where again I just want to emphasize, if you go through probability theory, that is where you'll better understand these concepts. Okay. Okay, so there is actually one more issue with this probability of improvement. Okay, does anyone know what issue? We can slightly even modify probability of improvement to result in even better. And as I told you, there is still ongoing research, which means issues are still there. Current, whatever method I am teaching, that also has issue. But yeah.
Yeah. So let's say you take that point as a probability like best candidate to explore further.
We'll see that thing. Let me finish one thing. We'll see a proper toy example.
I'm like trying to answer for the question you asked.
Which question?
Like, what is the problem?
Yeah, okay, yeah. Tell me, yes.
So if you take that point, then we saw in the previous graph that in this region the uncertainty is going down that red line, right? Yeah, going down that like best candidate we have. So in the next iteration, if we try this approach, we will not get any PI. It will be 0.
At this point it may be 0. It will be so actually the probability of improvement at these green points is actually 0. But for other points it will be non-zero, right? So this probability of improvement, you are not just computing at one point, you are computing at all x values, and then you are selecting that x value which has the highest probability of improvement.
So it might not be this point having the highest PI.
Yeah. Yes. So now even with probability of improvement, there is a issue which is, okay. So the main thing is, this is area under the curve, right? Area under the curve can be same for two point. It does not tell you about the quality of improvement. Okay. So what I mean by that is, I'm just showing it through an example here. These are two data points, two different x value. One x value is denoted by yellow, the other one is by blue. This is their distribution. This is your current best. So this plot is similar to this one that I have shown here. Okay. So this is your current best. This is the yellow mean for one particular point. This is the blue mean for the other data point. Okay. Which somehow the data points are such that the probability of improvement, which is area under the curve, is same for both of them. Okay. Now tell me which of these you think is a better candidate for which the experiment should be done. The first one is more confident. The second one is less confident. But the mu of this is very close to my current best. The mu of this is farther from my current best. And if I really want to talk about the quality of improvement, which one do you think is better, blue or? The mean for the blue is higher, right? So what you will see is that blue point is actually a better candidate. The way you can quantify it, you take the expected improvement. So again, expected improvement of this probability of improvement, and that's when you will get which one is better. In very simple terms, that part of the area which is farther from the current best is larger in this blue curve. Okay. So the probability of improvement, say you are slicing, say you are making slices here. Okay. So there will be more slices which are farther from your current best present in this blue curve, and that is why it's a better candidate. Okay. So it is something similar to the first moment. So expected improvement is like your first moment. So first moment, second moment, third moment, if you guys have heard about it. So your first moment of probability of improvement is better for this blue candidate, and that's why it's a better candidate than the yellow one. Okay. And if you take the expected improvement and then go about deriving your formulas, this is how the analytical expression will again come out to be. So you can see it has become slightly more complicated, wherein there is a cumulative distribution function. This small 5a is a PDF, the probability distribution function. And then one hyperparameter has also been added here, wherein if you so this is your say eta is your hyperparameter. If you increase this hyperparameter, the exploration will be larger. So you can control the trade-off between exploration exploitation by changing this hyperparameter. Okay, but the idea remains the same. We are somehow combining the uncertainty of the model along with the exploitation, the mean value, to select my best candidate. Okay. Now, given this is my definition of expected improvement, so expected improvement is this one. Okay, what I previously wanted to say is the expectation of probability of improvement. I think I said expected improvement. Okay, so now using that formula, if I then go ahead and again come back to my toy example. Okay, so what you see in the dotted line is your expected improvement. Everything remains the same. Along with that, I have also plotted expected improvement for all my x values. Okay, so wherever the expected improvement is higher, I will define that as my best candidate. So in this case, it happens to be this blue point. Then again, once I have found it, I do the experiment on it. I put it back into my training data, retrain the model. This is how the retrained model looks like. For this retrained model, this point now becomes the one with the highest expected improvement. And if you keep on going, you will see that the model actually found that this is the point where the maxima is occurring. Okay, it didn't get stuck. You see, also notice that the first 2-3 points are actually same as that of exploitation we saw in the exploitation. Okay, but after this, after the third loop, it knew that in this region my uncertainty is very large, and because of that, the probability of improvement and expected improvement will be larger. And because this is larger, it allows it to come outside that local maxima and explore further spaces and then continue to find newer regions which have better properties. Okay. One more important point, look at the prediction quality. The model is predicting that the value will be here, but the actual ground truth comes out to be here. Okay. So when model is exploring, okay, completely going out of its comfort zone, you may find that the errors are very large. Okay, so this point may be a little counterintuitive, but sometimes the model may be having large errors, but it still does the job of discovery. Okay.
Just question. So if you see the third case and if you draw that diagram, we'll get zero probability of improvement, right?
Where?
In the third.
So you are talking about loop 3?
Yeah.
Okay, so now which point should I talk about?
Any maximum point or like best point you could.
Like here?
Yeah, any horizontal line.
Yeah.
And if you take that prediction.
Yeah, so the probability of this expected improvement is plotted here. So you can see it is 0 here, near the training data it is 0, near this training data it is 0, near this training data it will be 0, exactly at that point it will be 0, but it doesn't show up in the plot because of scaling, right? You see it is drastically coming down. So the plot will actually be like this and then come up and then go. So I would have used a grid size, right? Like my grid is not coinciding with the point.
But
Your point is valid. At this point, it will be 0.
No, I'm talking about the square point.
Okay.
It is the next point you are talking about, right?
Yeah.
There the probability of improvement will be 0, right? Because
You are talking about this point?
Yeah.
Okay. Let's first come to loop 1. Okay. What is my blue point indicating? What is the definition of best now? It is based on expected improvement. It is based on the expected improvement. Earlier it was based on exploitation. So now expected improvement takes care of both uncertainty and the mean value. So the expected improvement actually is the largest. So this dotted line that you see is the expected improvement which is plotted. So expected improvement for this point is the largest. The blue point now here indicates that x value which is the highest expected improvement. So this blue point indicates that x value which is the largest expected improvement.
So according to the second formula that we showed.
Yeah.
But it will be 0 for probability of improvement, right? It will be 0.
No, why will it be 0? Why will it be 0? The probability of improvement, expected improvement will only be 0 at training data point, where green points are. Only at that point it will be 0. The moment you go far from from a training data, there will be some uncertainty. The moment there is uncertainty, there will be non-zero value. Yeah. One more thing that I didn't talk about, this thing. What is the, when does so this is a Gaussian. When does Gaussian become 0? Infinity. Okay. You get it? Okay. So Gaussian will become 0 only at infinity, which means that definitely at least some value will be there the moment you are outside training data. Okay. It may be of the order of 10 to the power minus 30, but still it is not 0. Okay. So now just showing one example. So this is one case, one publication. There are few concepts. So they were interested in finding new electrorestrictive materials. Okay. They started with initial known data set of 40. Their candidate data set was 6 lakh. So 600,000. So 6 lakhs was your candidate data set. Known data set is 40. So they use this expected improvement iterative learning strategy to come up with new materials in this material space, which results in the highest electrorestrictive coefficient, which is Q33. Okay. So they can change the barium concentration, calcium, strontium, titanium, zirconium. Okay. So these are concentrations they will change, and they will find the composition which results in highest Q33 coefficient. Okay. In what they did was, this active learning loop, they did it with different acquisition functions. So this is their iteration 1, iteration 0 basically is training data, iteration 1, 2, 3 and so on. So they use exploitation is one strategy, exploration as one strategy. Exploitation means best candidate equals to highest predicted value. Exploration means best candidate equal to highest uncertainty, highest sigma. Trade-off means expected improvement formula. Okay. And random means let's just randomly select one candidate from there. So they use this strategy, and what you can see is, so every batch they are making 4 compositions and doing experiment on it. Okay. So in first iteration they made these 4, they added that into the training data, and then make the models again, and then kept on doing this thing. And what you can see is the expected improvement is the strategy that resulted in identifying the composition which resulted in the highest Q33 value, in this case the measured strain. Okay. Okay. So few important points here. See how they identified a candidate which is better than their training data set. Okay. The training data set is only till 0.15, but they were able to go up until say 0.22 or 0.23 by using this strategy. Okay. So using machine learning methods, you can always find materials which are better than your candidate set. Okay. Please do not be under the impression that the model will not be able to tell something more than the training data. It will always be able to find it. Okay. and look at how their parity plot looks like. So this is the predicted from the model versus the actual measured one. Okay, the parity plot is not that great. Okay, you can see like the candidate for which the measured is around 0.23, the predicted value is only around say 1817. Okay, so the model need not be perfect for material discovery. That's another point I want to emphasize. Okay, even an imperfect model, the model prediction is very low, but still it is with the measurement, the associated ground truth value is actually high. What we really care about is the ground truth, the experimental value, and not whether the model predicted value was bad or not. Okay, so this thing is something which research is still ongoing. So like Vijit in my group is working on this. We try to define it accuracy versus discovery. Right, there is one concept of accuracy, whether my model is accurate or not, but there is this other concept of discovery, whether my model is able to find new materials which are good candidate or not. So we generally try to confuse these things, that a better model will result in better accuracy. These concepts are slightly different and they may not be exactly the same, but more research needs to happen in this area to have some lectures on it. What are the main points in this parity plot? So look at this point. So this is the point which has the highest experimentally measured strain, right? So this will have the highest Q33 coefficient. Okay, but the prediction for this thing is very low. So it is almost like 0.17. So the error of the model for this point is actually large. Okay, but still model is able to find it. So it is not just about model accuracy. There is something the material discovery can sometimes be slightly different from the accuracy can be different from the discovery process. Okay. Okay, so just showing for completeness, this is what the composition is, and then if someone were to intuitively try to do experiments in the lab, right, it's not possible. There are so many variables. How much to put, so many different possibilities, how to decide how much to put. So that's where this active learning strategy could be very useful in guiding how to do experiment. See how many experiments they did in total. They did 5 loops and 4 in each. So basically 20 experiments only they did in total. And within those 20 out of 6 lakhs, they were able to find a good candidate. Okay, so look at the power of this method. So we have done something similar in this area, active learning. This is in the space of peptides. In the interest of time, I will not go too much into it, but main thing I want to show here is what is on the x-axis is basically a traditional way how you will find your peptides. What is on the y-axis is the experimental observation. Notice how in this case we are looking for peptides with beta sheet formation. So whatever you see in the black is basically that the traditional way is also suggesting they will form beta sheet, and experimentally also you observe they form beta sheet. But whatever is shown in blue circle here, traditionally you will not find that. Traditional method will not suggest it will form beta sheet, but when you do experiment on it, they actually form beta sheet. And the reason we were able to find this new chemistry, this new candidates, is basically we went through this active learning route in which we made iteratively, we did experiments, and then we were able to find candidates which also form beta sheet, but will not be available if you were doing your traditional measurement, a traditional way of deciding what sequences to go for. My ability of the
Ability of the active learning models to decide the
batch size.
Yeah.
Okay,
the
you are,
batch size affect the
yeah, the batch size will affect. The batch size will affect your ability of discovery of the model. but the batch size is basically decided not from an algorithm perspective but from a logistic perspective. So for example, in this particular case, the peptide synthesizer that we have can make 24 peptides at a time. So if I do one experiment or 24 experiments, it is the same time. Okay. So in that way, you will just go for a batch size of 24 because you will gather more training data in the same time period, and so you will do it like this. Yeah.
And one more question.
Yeah.
Create a set and we take this mean and average, mean and standard deviation, and do the active learning, right?
Yes. So I talked in my first slide, you can always use bootstrapping and then ensemble methods to estimate uncertainty as well.
So bootstrapping is that you can take any model.
So bootstrapping is another procedure in which you randomly sample your training data. You sample from your training data and then estimate the uncertainty.
What about the model part, like this
Ensemble methods also you can use. Yeah.
Any sample of any method.
Yeah.
Particular kind of method.
Yeah. What is needed is you should have some uncertainty. What is the source of that uncertainty? It's fine. Obviously, that will affect. How that will affect, I mean, it will get complicated. But from this expected improvement standpoint, you need some variance, some uncertainty.
So let's say we are just using neural network. We can use different architecture of the neural network to predict different.
People use different architecture. People use same architecture, but then 10 versions of it. Okay. I have talked about this Bayesian networks. So there is a neural network which has Bayesian component automatically inserted as part of it. You can use that.
We don't have to make different architecture.
Yeah. There are all sorts of things possible. Yeah.
So all these peptides are synthesizable always?
Are they always synthesizable? Yeah. So that's a good point. I think there is a procedure by which you can make all of them. There are some which are more difficult to synthesize than the other, meaning they may take longer time or
Multiple steps are required for group peptide.
okay. So I am not too much familiar in this area. I just collaborate for synthesis of peptides. Yeah.
Model does not have any information regarding.
No. But from what I have been told, I mean, whatever sequence I tell my collaborator, he makes it. So, and actually in yield I don't know, but he is able to make it with certainty. Like he knows that this is what he wants to make and he gets that also as the output. Okay, another thing I want to talk about is, so far we discussed something where already some known data set was there. So say there is a problem whereas there is no known data set so far. Okay, you are starting from scratch, nothing is available. So that's where there are some other sampling approaches available. So one of them is Latin hypercube sampling, and this approach you can use to generate your first initial data set also. So first initial 10-20 points if you want to make, this type of algorithm is available. Okay, I'll just quickly note, generally when we perform experiment, right, what we'll do, say I have two variables in an experiment, what we'll do, we'll keep one constant, vary the other, then keep the other constant, vary the previous one, right? That's how we do. So basically we use something called as a uniform grid sampling approach. Although it may be good from a understanding point of view, meaning I know that this is the effect of my first parameter, this is the effect of my second parameter, it is highly inefficient. So if we are talking from a data driven experimentation budget standpoint, this is not a very good approach. Because see how much redundant the thing is. You are same parameter, you are measuring 3 times, right? So highly redundant sampling or such approach. This is where Latin hypercube comes in, wherein it tries to spread out the data. Okay, so it tries to spread out. I am not going into the detail of exactly the quantitative algorithm behind it, but it just tries to spread out the space such that as less number of possible experiments are repeated. Like you will not find any experiment with repetition in the parameters. Okay.
What is parameter mean here? Features?
Yeah, it will mean features. If you are doing experiment, it could be something like temperature, solvent concentration, which can also be your features to the model. Okay, and when you do this, you basically have a better estimate of your sampling of your design space. Your total material space is actually better sampled using this Latin hypercube sampling approach. So what is my suggestion for anyone, if you want to start using, if any one of you is experimentalist or you will later collaborate with an experimentalist, and how you should start approaching using this method. First, you identify what is my design space. First thing, that's what you have to do, that this is my design space that I'll be working with. Then you can use your Latin hypercube sampling approach to select some of the initial experiments you want to perform. If you already have a data set, then you can skip this part. Once the data set is known, then you do your machine learning model training. Whatever model you want to try, you first identify which are the models which are resulting in most accurate results. Once you have identified the model, you go for this iterative active learning approach, wherein you also account for the uncertainty in the model prediction. Okay. Yeah, with this we'll stop here, and then in the next lecture, next we will do this hands-on tutorial, wherein we'll compare all these 4 different acquisition functions. So exploitation, exploration, expected improvement, and some random search. We'll compare these things.